You ever have that feeling? You're first in line for a raffle and you just know it's bad luck? Or maybe you're last, and you're thinking, well, all the good prizes are definitely gone by now. Our gut feelings about chance, about probability, they can feel so real. But what if I told you they're often just wrong? Today, we're going to look at how the actual math of probability can be totally different from what our intuition tells us.
So let me introduce you to Aruna. Picture this. She's in a classroom, and the teacher has a box full of folded paper slips, or chits. Aruna is the very first student to pick one, but she's not happy about it. She is absolutely convinced that going first means her chance of getting the one special chit, the one that says Basil, is basically zero.
And then, all the way at the other end of the line, we have Zarina. She's going last, and she feels just as unlucky as Aruna. Her thinking is, well, by the time it's my turn, somebody else will have for sure already picked the Basil chit. It feels completely hopeless.
So, what's the deal here? Is Aruna right? Is Zarina? Could they both be right? Or maybe neither of them are. This is the big puzzle we're going to solve. In a totally random draw, does your spot in line, whether you're first, last, or somewhere in between, actually change your odds of winning?
Okay, let's really set the scene. We've got one teacher, a class of 40 students, and one box. And inside that box are 40 identical, perfectly folded paper chits. Only one of them has the name Basil on it. Every single student is going to pick one. The question is simple. Who has the best chance?
To figure this out for Aruna and Zarina, we can't rely on feelings. We need facts. And to get to the facts, we first need to learn the basic language of probability, the language of chance.
Everything starts with what we call a random experiment. Now that sounds fancy, but it's really just any action where you know all the things that could happen, but you can't say for sure what will happen. Think about flipping a coin. You know it's going to be either heads or tails, right? But you have no idea which one it'll be until it lands. That's a random experiment. In our classroom draw, it's the exact same thing.
And each of those possible results, we just call that an outcome. So when you flip that coin, heads is one possible outcome. Tails is another. See? Simple, right? So if an outcome is just a single possibility, the very next thing we have to do is make a map of all the possibilities. Before we can figure out the odds of something happening, we have to know every single thing that could possibly happen in the first place. And that complete map, that master list of every single possible outcome, has a name. It's called the sample space. It's not just some of the possibilities, it's the absolute complete list of everything. And you can see how this works with some really simple examples. For a coin toss, the sample space is just heads, tails. That's 2 total outcomes. If you're rolling one die, the sample space is 1, 2, 3, 4, 5, 6, which is 6 total outcomes. It's just a really organized way of seeing the entire playing field. But what happens when things get a little more complicated? Like, what if we toss 2 coins? Well, for each result of that first coin, you've got 2 possibilities for the second one. So when you combine them, you get the full sample space. Heads heads, heads tails, tails heads, and tails tails. A total of 4 possible outcomes.
Okay, so we've got our sample space. That's the list of everything that could possibly happen. But most of the time, we don't really care about everything. We care about one specific thing happening. And in the world of probability, that specific thing is called an event.
An event is really just a group of outcomes that we're actually interested in, the ones we're rooting for. So if you're betting that you'll roll an even number on a die, your event is just the outcomes 2, 4, 6. It's just a small group that you've pulled out of that bigger sample space.
Let's try this with a bigger example. Rolling 2 dice at the same time. Suddenly, our sample space just explodes to 36 different combinations. Now, let's define our event. Let's say we only win if the sum of the numbers on the dice is a multiple of 5. Looking at this whole grid, which of these combinations are the ones we're hoping for? And there they are. The highlighted squares are our winners. We've got a 1 and a 4, which adds up to 5, a 2 and a 3 and a 2, all the way up to 4 and 6 and 5 and 5, which both add up to 10. If you count them up, there are exactly 7 outcomes that match our event.
So check this out. We now know the total number of things that can happen. That's our sample space. And we know the number of things we want to happen. That's our event. Now we can put it all together with one super simple formula to find the actual probability.
And this is it. Don't let the letters fool you. It's incredibly simple. The probability of an event happening is just the number of outcomes you want, divided by the total number of outcomes that are even possible. is just what you want over everything that could happen. That's it.
All right, let's take this new formula for a quick spin. If you roll a single, standard die, what's the probability that you land on a prime number? And remember, for a die, that means a 2, a 3, or a 5.
First step, how many outcomes are we rooting for? Well, the prime numbers are 2, 3, and 5. That's a total of 3 favorable outcomes.
And next, what are the total possible outcomes when you roll a die? Well, that's easy. It's 6.
And now we just plug it into the formula. We have 3 favorable outcomes divided by 6 total outcomes. That's 3 over 6, which simplifies down to 1/2. So your probability of rolling a prime number is exactly 50%.
Okay, we've done it. We have all the tools we need. We understand random experiments. We know what a sample space is. We know what an event is. And we have the formula for probability. It is finally time to go back to that classroom and give Aruna and Zarina a real mathematical answer.
Let's start with Aruna, who goes first. For her, the math is pretty clear, right? There is 1 Basil chit she wants, and there are 40 total chits in the box. So her probability is 1 in 40. But here's the mind-blowing part. The exact same thing is true for Zarina. Before anyone starts drawing, from a pure mathematical perspective, every single person in that line is facing the exact same odds. There's 1 winning chit and there are 40 total chits. That means everyone, from first place to last place, has a 1 in 40 chance.
And that is the crucial point here. As long as the draw is actually fair and random, every single one of those chits has an equal chance of being picked by anyone. Your spot in line literally does not matter. It feels like it should, our brains tell us it should, but the math is crystal clear. Aruna and Zarina's worries, they were all based on intuition, not on reality.
So, this brings us to a much bigger question. Now that you know how wrong our intuition can be about a simple classroom draw, where else in life is this happening? Think about it. In the lottery, in stock market picks, maybe even in the small choices we make every day. Where else might our gut feelings about chance be quietly leading us astray?